Let's continue our discussion in chapter 1. Last time we talked about how we're going to do the histograms and what do they represent. And today we're going to look at different ways of visualize the data. So first of all, let's take a look at this table. This table gives you a set of 40 pipes and their measurements in interval from 3 to 3.9, 44.9, and so on. So this table, first row shows that there are 13 pipes whose length is between 3.0 and 3.9 feet. And between 4.0 and 4.9, there are 23 of them. 5 and to 5.9, there are 3, and 6 to 6.9, there is 1. Of course, we can use this data to create a histogram. That's not be a problem. On the other hand, we also have other ways of visualizing it. First of all, let's introduce this cumulative frequency diagram. The steps of creating the cumulative frequency diagram would be, first of all, we calculate the cumulative frequency to the left and right-hand boundary in each group. To do this, we're going to add the group frequencies one after another in order, starting from the leftmost group. And then, if necessary, we're going to change the cumulative frequencies to percentages, and then we choose the scales for the axes, and then we're going to plot all the points, and then join the plotted points with line segments. So this is how we're going to do, and finally we label the figure clearly. So we're going to do the first step here. So this is the raw data given, and now we can calculate the cumulative frequency. So we're going to use these boundary points 3, 4, 5, 6, 7. And now we're going to ask, hey, how many measurements, how many pipes are less than 3 feet long? The answer is none of them. Every one is at least 3 feet long. So here the cumulative frequency is 0. Of course, 0 corresponds to 0%. And secondly, we ask, hey, how many measurements are less than 4 feet long? The answer is there are 13 of them. That's where you find from the first group. And that is 32.5% of 40 pipes. You use 13 divided by 40 and then times 100%. And how many are less than 5? Well, now we need to add the frequencies because in both groups, the pipes are less than 5 feet long. So we have 13 plus 23, which gives you 36. So that is 36 out of 40, which is 90%. And if you can ask how many measurements are less than 6, the answer is we can add another 3. So everyone here, all these 3 lines need to be added. We can add another 3 to give 39. That's 97.5%. And finally, if you can ask, hey, how many is less than 7? The answer would be that is everyone. Everyone is less than 7, and therefore the cumulative frequency is 40, and percentage is 100. So in order to visualize this, we're going to use the cumulative. We're going to use the whiteboard. I'm going to pull out the whiteboard, and we're going to draw the cumulative frequency diagram like the following. So first of all, you're going to draw the axes. So we're going to start from, let's say, here, and we draw our horizontal line represents the horizontal axis. This doesn't have to be super long. And let's say this is, and then a vertical line represents the percentages. So vertical line should represent the percentage. So let's say right here. So here, let's say we're going to do a 0 right here, and 1 is the length, 2, 3, 4, 5, 6, 7, 8, 9, and that should be more or less enough, but let's do 10. And so this is our x-axis. And then for this one, we're going to do a percentage. So let's say this is 20%, and then 40%, and then 60%, and then 80%, and then 100%. So this vertical axis represents the percentage. Of those pipes that are less than X. So first of all, that's based on the previous table that everything is less than, nothing is less than 3. So here at 3, the cumulative frequency is 0%. And then at 4, the cumulative frequency, which is calculated, and now it increases from, let's see here, up here, and from you see here, look at this one, from 0% to 32.5%. So we're going to plot 32.5%. So it's just a little bit about 30% line, 32.5%. And now at 5, and it increased to 90%. So it increased all the way up here. And then at 6, it increased further to 97. It's almost 100%. And then 100%. Actually, 5 is here. So at 6 is here. So it's almost 100%. And 7 is 100%. And then we're going to connect the dots. But before we do that, remember that everything under 3 would be 0. And then everything above 7 would be 100%. Or if you ask, hey, how many pipes are less than 8 feet long? The answer is everyone. That's everyone. And then finally, we're going to connect the dots by straight line segments. So connect the dots. Here's. And then this will give you a way of how this measurement increases. So this is what we call a cumulative frequency diagram. We can also do what we call a reverse cumulative frequency diagram. Namely, we do everything backwards. So what do we mean by that? Instead of computing the measurement greater than or equal to, or less than or equal to, we can also do greater than or equal to. So in this case, we start from the larger number 7. Everyone is less than 7. So if you ask, okay, how many pipes has length greater than or equal to 7? The answer is none of them. Nobody is greater than or equal to 7. So the cumulative frequency is 0. The percentage, of course, is also 0. And then how many measurements are greater than or equal to 6? That would be the only one. So that's 1, which is 2.5%. How many are greater than or equal to 5? That's this 1 plus 3 in both groups. So that's 4, which is 10%. And then how many is greater than or equal to 4? So that would be all these 3 numbers added together. That's 27. So it's 67.5. Finally, how many is greater than 3? Greater than or equal to 3. That's everyone. So that's all 40 of them, or 100%. So we can basically plot a very similar but different table graph like this. So we're going to still use the axis like this. 0 and 1, 2, 3, 4, 5, 6, and 7. And then you can do a little bit more, 8, for example, 9. And now you have 20%, and then 40%, 60%, 80%, and 100%. And also notice that this is the x-axis, and now this is the percentage. Of those measurements that's greater than or equal to x. See, there's the difference here. And again, I'm going to plot dots, and at 7% is 0, it's nobody. At 6, at 7 it's 0%. At 6, it's going to be 2.5%. So go back to here, that's 2.5%. That's very little. Small dot right here. And then at 5, it increases 10%. So it's about 10% right here. And then it's about 10% right here. And then at 4 is 67.5%. So it's above 70%, below 70%. And then it increases to 100% at 3. So we're going to connect the dots, and then have this horizontal lines like this. And after you connect these dots, that's what this graph would look like. All right, so this is how we draw a reverse cumulative frequency diagram. All right, and can this thing be done in R? The answer is yes. Depends on how complicated you want things to be. If you understand simple R code, let me just erase what I had before. And so first of all, you define these. So let's just define this as your x as a vector. The c is simply to define it as a vector. And then the code we're going to do is to plot the ECDF of x, and then this will give you a graph that looks like this, and I can make it a bit larger so it's easier to see. So if I make this graph larger, this is what the ECDF would look like. So here, this is the cumulative frequency diagram. You might say, hey, this is different from what we have drawn. The answer is yes, but this is a different way, but similar concept of represented data. If you want to learn a little bit more, there is actually a much more complicated code, which I don't even recommend you to memorize or to understand. And this one will give you a better diagram, and it's up to you if you want to try it or not. But this is definitely not required. You're not required to know this code. You're not required to understand what is data frame or what is the ggplot or what is their the sort of data, etc. All right, so I'll encourage you to spend some time doing this exercise at home. This is example 4 on page 16 of the textbook, and make sure that you practice this before our next class. And let's talk a little bit about the connection between the histogram and the cumulative frequency diagram. If you have a histogram that looks like this, you may say this is not a histogram, but you can visualize this as a smoothened version of it. Let's say you have extremely short bars, and then narrow bars, and then they would look more or less like this. And if you have a normal distribution, which means you have more data points in the middle and fewer data points at these two ends, then the cumulative frequency diagram will form a very nice curve like this. If you have a gap, namely you have some intervals with no data points, and then this will be reflected as a flat line segment because nothing is increasing, the cumulative frequency diagram would have flat. On the other hand, if you have a lot of data points in one small interval, and then the cumulative frequency diagram will go up very quickly. This is a steep line, or in other words, if you use the language slope, the slope is very big. Well, here, this is not going to happen, at least unless somebody made a mistake, which is the cumulative frequency diagram shouldn't go down. If it does, that will correspond to a negative measurement. Think about that. You're basically saying, hey, between this and that value, the number of students is -5. And the answer is, that doesn't make sense. So since this doesn't make sense, and the cumulative frequency diagram should never go down, if it does, something is wrong, that's a mistake. Well, let's talk about a few notions related to large numbers of measurement. Normally, we don't use this for small number of measurements. If you only have 5 measurements, then we don't normally talk about this. But if you have for dozens, hundreds, thousands, or even more, and then it makes sense to see how the data is divided. The first quartile is the point where you draw the line between 25% of data and 75. So if you're at the first quartile, you roughly know that 25% of data is below you and 75 is above you. That's the simple. The second quartile, which is the same thing as the median, and actually the median is a more common name, is where the number divides the distribution into 2 halves. The third quartile is where it divides between 75% and 25%, 75% versus 25%. And these 3 numbers together will divide its distribution into 4 equal parts. The interquartile range, which measures the distance between Q3 and Q1, is denoted by IQR. Just use the Q3 minus Q1. For a set of points, if you have a large interquartile range, that means the data is more spread out. You have a larger distance between Q1 and Q3. If you have a very small interquartile range, IQR, that means your data is more condensed. And finally, let's look at how we do this in things in R. Let's go to our R. And here, once you define X, what you can do is to do the quantile of X, and then this 0% gives you the minimum number. 25% gives you Q1, 50 is the median, 75% is Q3, and 100% is the largest number. And then you can use Q3 minus Q1, that's those numbers that's defined, to get the interquartile range, in this case 8.5. Or a more direct command is simply use IQR of X. You get exactly the same answer as expected. Well, thank you very much for watching. I will see you in the next chapter.